Connected? Yes. Last time. Oh yeah, that's the game we're in. Remember what we did 2 weeks ago? Well, time dependent, if I'm not correct, if I'm not mistaken, correct? The transient fuel problems, right? We wanted to do. I looked at the explicit on a difference method. And then we had a look at the implicit and the Crank-Nicholson. Right? We basically have we're gonna try to solve the problem here. We have a uniform play layer 8 deep. So let's get on with that one. Oh, thickness. We have CV 110 meter square per year. An increment of stress 10 kPa, meter interval 15 years. Yes. And two-meter interval. So we're looking at the degree of consolidation after 15 years. Okay, let's do our profile. So we will have different problems. The first one will be explicit. Let's use it with matrix. And we're going to do with it. Okay, so uh, let's put initial condition. We'll put the time. Yes, we could put the time in columns or we could put it in rows. Won't really matter one way or the other. And let's look at how we would do it. So how does the explicit method look like? So we solve here. We're looking at the explicit method and we said that it looks like um, basically we are trying to solve for our node I at the next time step. So we look at the previous time step and in this case, we've put everything that had the same previous time step on the right side and the next time step on the left side. And we end up with the variable like this. As long as we have a uniform K, obviously. And if K is variable, obviously we pull this out of the we have to pull it out of sorry, the K term and we have uh the terms equal to each other. So we'll have to do it a bit differently. Anyways, right now we're looking at one case with uniform K, so we're going to calculate R once. And we express it in terms of the hydraulic conductivity times, or in this case, our value of CV, sorry, times delta T over delta Z squared. So it's related to the square, it's inversely related to the square of the interval between the values. And at the same time, it is also related to directly related to the time interval. So the smaller the time square, the smaller the interval we need to establish to maintain to ensure that R remains smaller than 1/2. So in our particular case, what we are going to say here, we're gonna calculate R. And we say that this is CV. Yeah, so first let's call our delta Z. We said that's equal to 2 meters. And we have years, so we'll have to calculate what because that's meter square per year, the CV. We then need to find which value of delta is. delta X, delta T we need. Okay. So we know that R is equal to CV delta T over the over delta Z squared. That means that to find delta T, we need to say, so, and that must be R must be smaller or equal to 1/2, right? But as I said, remember that what I said last time. It works for now, but the real test is that the entire expression between the brackets must be larger or equal to 0. Okay, that's the real test. So for a uniform soil, 1D, saying that the R is smaller or equal to 1/2 is good enough. But once we start going in 2D, first the values of CV may be different in different direction, right? You may have different coefficient of consolidation or hydraulic conductivities or thermal diffusivity in different directions. And so you might end up having different values of that are in different directions, but whatever is in this term must always be larger or equal to 0 for the explicit finite difference method to work. But for one material, we're setting that as 1/2. So for this to be equal to smaller or equal to 1/2, what we are going to say is that delta T will be smaller or equal to delta Z squared divided by 2 C. Okay. So that will be our requirement that T must be equal to, so let's give this a variable name. Oops, not zeta, but Z. Okay. And this one will be called delta. Yeah. Keyboard here, but I think I'm good. Delta T. So that's delta T, that's equal Z. And therefore the delta T must be delta Z squared divided by 2 times C. So 1.8 years. Basically 21.8 months. So to make our life easy, we could say that delta T is equal to 1 year, right? Because that's in years. Since we have meters square per year and meters, that has to be years. And so 1.8 is a little bit awkward. We can go to 1.5, but why not make it 1 year. It needs to be smaller or equal to that. So by choosing 1 year, we make a number which will make it easy for us to follow evolution. Okay? So we'll call it 1 year. And we're still respecting the minimum. So we should be safe to do this kind of, we should be able to converge with the explicit finite difference. So we will use here a finite in terms of row. So we will go and have 0 that plus delta plus delta z. And we're incrementing up to 8 meters. I agree, it's pretty small, but more ambitious. But we're gonna get a coarse looking, a bit coarse looking table, but it should be okay. However, if we had used a value of 1 meter, say, you would have to use 0.4 years. So 5.4 months, so maybe at best 5 months, so maybe I would have gone 2 months or something like that. So let's be happy now for 2 years, and we'll deal with it later on. But whenever you have to change your, physical grid, your space grid, remember that you need to also adjust your time. Okay. Now, with the explicit method, if you don't do it, you will see what happens. It will not converge and it will be obvious. You will get some solution that makes a bit more sense with the implicit method, but the error may be large. Okay, so it's always a good guide to use this. Although the implicit will converge, remember that this is a good guide in terms of how big your time step can be, even when you're using another method. It's not a bad guideline. Even if you're using finite element, it's not bad to think of it in terms of this explicit method. To give you an idea, if for your time step, your mesh may be too fine for the time step that you're thinking. There might be some errors implied within the calculations that you're not aware of. So here we say 1 year for now. So here we're gonna have the time. That's obviously the Z. Time starts at 0. We said that our pore pressure, excess pore pressure was 10 kPa, right? That's the excess. So we will obviously have some hydrostatic pressure, but let's say we put a uniform load, wide area, we increase the total stress by 10 kPa, so that is the stress everywhere. Now, I should say, Carl, that is not, my real 0 will be after this, okay? So that's blanket, but at the boundaries, I have an instantaneous reaction, right? So I'm gonna set my boundary conditions at the true 0 here. That's the time-dependent 0. This is a idealized 0, but really my boundary conditions are here, right? So I have instant dissipation of pore pressures at the boundaries. Right? Now, what happens at the other cases? In the other cases, well, we have to look back at the equation that we had here, where we have UI equal R, basically the sum of the R's, plus of the two nodes, plus 1 minus 2R of that given node. Okay, so excuse
excuse me, you will use 0, 2, 4, 6, 8. Those are as the nodes. Yes, this is the thickness, 8 meters, but we have to work on nodes.
Yes, those are the nodes. So basically, I'm assuming that I have a ground surface. It's 1D, right? So I only have along one line right now. Yeah, so we have along the center line, we are creating a series of sample points. We have a 0, 2, 4, 6, and 8 meters. We have these sample points at which we will measure the excess pore pressure. So instantaneously, what I get for the excess pore pressure only, I get an increase in pore pressure of 10 kPa. Continuously. And after that, I will get some dissipation. So that I expect this to be I expect at a given time t in between get this curve that will dissipate over time. And the over time, I will expect it to be coming down like that. Oh. That's what I expect visually. So we'll see if we get something like this. Okay. So I have an instantaneous increase in pore pressure, but immediately at the edges, I will have an instantaneous also decrease of pore pressures right at the boundaries. So this is what that represents. How it changes though, it depends on this equation. So at UI, I have R, so I have to calculate the value for R for my little equation. Okay. So here, let's call this R. And R is equal to CV times delta T divided by delta Z squared. R is equal to 0.375. Okay, so we come here and we say it's equal to R times from the previous step. At the previous step, because it's the explicit. Sorry, I'm starting here. So at time 0, I have 10 everywhere except at the edges. Okay, this is instantaneous. Now at 1 year, so I go this plus the time increment. And plus delta t. And I could insert here so this is the x or the z value. And now here I have my change in pore water pressures. So I say At the boundaries, my boundaries are controlled. Here I say I have R times left node plus one minus two times R times my same node, but the previous time step plus R times the following node. So we're looking at 15 years. Let's here, it's one scatter. Those, those. Let's label. I didn't forget it all. Oh, I forgot the X value. And never mind, should have put this. Let's get rid of this row. It's gonna complicate things otherwise. So. Much better. Yeah. This is the X, this is the. Let's see the problem. Let me fix my boundary. Now, they should all look okay. Can be done, I swear. Insert chart, XY scatter. Those. There you go, that looks much better. So, obviously that's in time. Start with, obviously because I have 2 meters, right? So the resolution is not good, but should really get a constant line and very sharp. But we can see that the general shape is not too bad, right? That's what I expect. And I bet that if I were to, let's see what it looks like, chart time. No, it's not, doesn't look good for the first one, which is a straight line there. But for the other ones, I mean, these are basically the shapes that we kind of expect, but will not be the best either. Yeah. So it makes sense, right? At least. Before we go to the implicit, yeah, so we get the shape that we wanted. Obviously, that's tipped over on the horizontal, but it's the shape we wanted. Before we move on, we're gonna look at how we expressed. So this is a memory efficient approach because I have one row that has the data of the previous step and I calculate the next step. And if I was doing this programmatically, I could just switch the content of the two rows, right? And just have twice the number of nodes in terms of RAM. That would be all that I would need to execute this. I could go, however, say that I'm using Octave on my phone. Octave is optimized to because I don't have Apple, so I can't do it actually. Octave is optimized or Maple. Did I say Maple? I mean MATLAB is optimized to work on matrices, right? So if you could express the same thing as a matrix, okay? So what do we have on the left side? We have an equation, then we have R one minus two R and UI R. So if I were to have something in the form one for the first row, say, right, and then one, he said that it was one, and one minus two R. Right, kind of in that form. And what's on with me is a diagonal matrix. Okay, so we end up with something of this form. So I can say that this is the matrix, and here I have node 0, node 1, node 2, node 3, node 4. Okay. That's the number of nodes, right? I have 5 nodes. If I remember correctly.
6, 8, 5.
5. So, 0, 1, 2, 3, 4. So I have this matrix then, I can use it now to represent, so this is at time, at the past time. Okay, so this is all on the right side of the equation. And I can say, well, U0, U1, U2, U3, U4 at next time is basically equal to equal to that matrix times that vector, right? So I don't have to do any inversion of matrices or anything. It's just a straight up matrix that I multiply by by my vector. Sounds good? If I multiply this vector by that vector, I will get my matrix. So we'll start and do the same thing that we did before. Let's move this to the side. Let's do what we had here. We had 0 equals that plus delta delta Z. And in terms of T and 0, we had 10, 0, 10, 10, and 0. And that's that plus delta T. So this time we're going to set it up in terms of our little matrix. Okay. And these are two. Well, there are two boundary conditions, but they will be applied to the previous one. So we will define our matrix here and we will give it a name. All right, N. So this is 1 minus 2 times R. Find this as matrix N. Okay, so that's matrix N. So I will do my matrix multiplication, but it's the transpose. I need it to be vertical matrix. So I will say M multiply my N value times the transpose of the previous row. Oh, and I should transpose the result. Because I want it, sorry, I want to transpose and multiplication of N and the transpose of these. Okay. Now, let's copy that. I should get the same values that I did previous one after 15 years. Oops, that doesn't look right. Wrong. Supposed to be going down, right? Not going up. One minus 2 times 5. Let's see, 0 and 0.
Professor, is it R or what?
Hmm?
Is it R?
Oh, that's one. That's right. It's 1. It's R. It's 1 times R.
Yes.
It's tight. It's long. It's late. It's 1 times R. Good catch. Okay, that makes more sense. So 0.8658 And we have 0.8658. Looks good. Right, and the other values are all the same also, I expect. That's 1 to 2. Let's see. So it's all the same values. Okay, so we have a working system even with the matrix. So this is the matrix that you would have to to use. Okay? So we look at your term here. So obviously R times the neighbors and 1 minus 2 R times the central value of the previous instance. So that will become useful to see it in matrix form, because when we go to the implicit method, we get something different. Right? In the implicit method, we have the one we want to solve for is this one. But inconveniently, that one is on the left side with all kinds of other neighbors. Okay, so I don't know what this one is, but I need to solve it. So if you look at it, it has a form. It is in the form minus R, 1 plus 2R minus R based on the neighbors, but on that side. Okay, so it's that matrix times the future one is equal to the previous one. The problem is that I know the previous one, right? The one I want to know is this one, so I need to get rid of my matrix on this side. So how do I get rid of the matrix? By saying my solution is the inverse of the matrix times the previous vector. So we're coming back here. We're going now to the implicit. Let's copy most of this. Go to the implicit page, paste it. This time we're gonna change our matrix. Okay, so it will be very similar. We will change the name. It's going to be minus R on the sides, not R, but minus R. And the central one will be 1 plus 2R. Right?
So here the value of R still less than R. Still the value of R be less than R half or more, because we put like condition less than or equal R.
Now we don't have that criteria, but we're keeping the same time interval. But as I said, it's not bad to stick to that value. You'll see what changes if we change that value, how far away the values become. But first, we'll compare it with what we have. Okay? So we define our values. Okay. And now this is matrix M. And here we will have transpose of the multiplication of the inverse matrix M inverse, right? So we say transpose of the multiplication of M inverse matrix M. And the transpose of the previous values. So it's going down, so no glaring mistake. Okay. And this time, if we do the same thing as before, And we put the graph, XY scatter. Data is in rows. Data series in rows. The first row is labeled. No, the first row is not labeled, sorry. Now the first row will be labeled. XY scatter. There. So it looks good. Notice one thing. One big difference from this one is that this is no longer sticking to the first value, right? It's detached. So it's able to converge faster. In that sense, right? It predicts in the future. It looks towards the future rather than the past. Okay. And so that we'll take but we have an NT, so anyway, so that's a definite. Let's get rid of this series. We have there our time series projected in the future and a bit more organic, I would say, way of doing. So this is our projections in terms of the implicit method. Yeah. The Crank-Nicholson is a little bit different than both of the other ones. Because Crank-Nicholson was an intermediate time, right? We were looking both at the past and the future interval. And so what we end up with, when we isolated, right, it was this thing where we have R/2 on both sides, basically. We keep basically both matrices. Except instead of R, we get R/2 in our expressions. So because that's a little bit cumbersome to use, we're going to define a new variable called rho. And rho will just be R/2, basically. And if we define a variable called rho, we get very similar matrices. Okay, except that instead of R, we're dealing with rho. And so we have these two matrices where we have the matrix times our next value is equal to the previous matrix times the previous. So now we have to do a double multiplication of the inverse of this one times that matrix times the vector of the previous value. So let's set up our little spreadsheet to do just that. First, we're going to define a new variable called rho. And that will be equal to R/2. For the Crank-Nicholson, this one Copy this for now. We will have two matrices, right? Frank Nicholson is going to be for Frank Nicholson, we're gonna do this minus rho. Rho. Yeah. Rho. Okay, now it works. So minus rho, 1 plus 2 times rho. And that will be minus rho. The zeros everywhere first. Easier. Okay, and that's the M for Crank Nicholson and the M matrix for Crank Nicholson. Again, we'll start with zeros everywhere. And so we put one there, and here we have. Oh. And 1 minus 2 times rho. We'll call this MC and NC as matrices. And so here it's a transpose of mat multiplication of matrix inversion of MC. And the matrix multiplication of NC and the transpose of the previous vector, right? And multiplication, multiplication and transpose. Let's do our little graph thing again. Graph. This was scatter. Next. Those. It's good. No. Okay, so let's have a quick look at a quick compare first. After 15 years, we have 1.06. With the implicit, we had 1.2. And explicit, we had 0.86. So one thing that we can see is that we're getting somewhere in between in terms of predictions. Okay? It's like an average. Basically, it's essentially an average of the other two methods. At every point in time, if we look at the Crank-Nicholson, we'll go a little bit more like the average of the other two. Let's put our figures together. They're the same size. That's it. That's it. That's it. And Crank-Nicholson. So you can see that the Crank-Nicholson is a kind of a little average in between the two. And interestingly enough, despite the same time step, we get more of a reduction in pore pressures in in the explicit method in this case, although it starts with a more of a lag. Now, what happens if I use a time step that is bigger, say 2 years? Okay. This is what it starts to look like with the explicit method, and the reason why we have the criteria that it should not be more than 1/2. Okay? Think of it, it's a little bit related to the speed at which a signal can move through the medium, right? CV controls the speed of the movement of the information. And so when you're trying to predict something faster than the information can propagate through your numerical scheme, and you get these things. Now these, because of the nature of the matrix inversion, the fact that you're predicting in the future, they are much more stable in terms of the time. But it doesn't mean that the values are correct. And as you can see, okay, so we're going to a time step that is 2 years, so it's 3 years. So what do we get at 15 years? And see it here. It was 1.2. It's not too bad. It's a little bit comparable to what we had at 15 years before. It's 1.29. And before we used to have 1.28 at 15 years. So it's not too bad yet at this point. So you can get away with a little bit more of bigger time steps when you're dealing with other methods, but keep in mind that they do not show you when they start breaking up the way that the explicit shows it to you. The explicit is very obvious when your time step is too large. Okay? The other methods will look okay, but what do the numbers really mean? Right, so when does it stop being reliable in terms of values? Let's say 1.28 is what we get, if we had 5 at 15 years. See, we get now 2.03 at 15 years. Right, it starts to be much more different. If I say 15 years implicit, at 15 years 3.39, right? When we had 1.298. So doubling the time step, I had good predictions. Here, it still looks nice, but the numbers, are more than twice what they were when I had the finer time steps, right? So it is incorrect, but in a way that doesn't look as bad. You know what I mean? So you do want to, so that's the, in a way, and the Craig Nicholson actually breaks down at some point. It's an average between the two, so at some point it does seem to vary. It's supposed to be stable in time, but anyways, the implicit is, does have a dangerous kind of effect in that it will not let you know that the values are wrong. So although the explicit method is more sensitive in that time step, here, that one, 15, 1.0, it's not too bad, it's comparable to the. So keep that in mind whenever you are using these values, okay? So you still should use the criteria for the explicit method for other methods, even though you may not need to adhere to it, but it gives you an idea of what time steps would be good or not. And the same applies to your finite element, right? The finite element, like the implicit method here, it will not show typically something that doesn't converge like this. But keep in mind that it has the same basic limitations, right? Because information needs to propagate through your elements, through your mesh. So depending on how small your elements are, you can compare the smallest elements to that mesh size here and see how stable to expect. You can make that time step bigger, as we've seen, right? And it will give a reasonable result, but there is a limit. And it will never be obvious what that limit is, unfortunately, before the numbers don't make sense anymore. So keep that in mind and think about this, the explicit method criteria as a general guide as to what will make sense. We'll take a little break here. Okay. And we'll continue after the break. We'll drink. We won't be too long after the break. I don't think, because it's already 8 o'clock. It's 8 o'clock. Have a break, and then we'll start the next section, which is oh yes, the strip footing. We're gonna start talking about the strip footing and how we're gonna handle that solution. As we saw the problem in 1D, now we're gonna look at the problem in 2D.
And you said 2D, it will not work well. Explicit method, that's right.
The explicit method will work in 2D.
Said that.
Actually, in 2D, we will kind of stick to the explicit method because it's easier to implement in 2D. Because the matrix, if you have to build a matrix in oh, maybe, no, sorry, I think it's still 1D. Sorry. I think the question we are trying to do here, yes, we're still expressing it in 1D under the center line, and then we can expand this one in 2D. We're still gonna start it with 1D. But we're gonna stick to the center line. Yeah. The difference is that the stresses are not going to be linear this time, right? I think that was the intent of this example. Anyways, we'll get started on it, play with it, and then later on we'll expand into 2D. And we try to progress a similar example. Expand just to see how it's implemented. But you saw how it looks like with just the constant stress increment with depth. So, more interesting changes. Yeah, the question, no, no questions. That's suspicious. You know, without your laptop, you look naked.
I know, I know.
You look uncomfortable with your body. You don't know what to do with yourself. Is it the same thing at home? Do you traumatize your children when they see you without your laptop?
Laptop, C, switch. Yeah,
You mean switch the Nintendo Switch, or you just switch from
I
one
just
to the
switch
other? Okay. Anyways, I'll see you and
laptop if they're watching TV. Hmm? 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 The lecture 2 is just the definitions, and then lecture 3 was what we did the week before I left. Yeah, I saw it. Yeah, a 3-node. Oh, yeah.
So, Sinal is use the image you are. Let's say,
Yeah.
okay, it's the.
Yeah.
Yeah, it's like similar principle.
Yeah.
Just people have this. Okay. Which one with the shorter?
I don't understand how he would ask.
We have to be. It's the allocation of resources.
Yeah.
But we have to be.
Yeah.
You get it from the Excel.
Yeah.
This time we have the.
Oh, I see.
In like simple, you do benefit for each.
And we have to find the flow.
And
Okay.
like just one difference will to get the highest value. Just
Yeah.
few. This is the
Okay.
principle.
Like the highest flow for.
Then we'll take, let's say you get the highest from this node and we will carry over. So let's say 1, 2, 3. The highest is the 3. Once you need to this 3 plus the values of it. These difference.
Yeah.
Yeah.
Yeah, we have to ask him more tomorrow. I saw the 2 other examples, 23, 24.
24.
What?
It's the assignment.
Yeah. The 23 seemed. This was.
Whatever you will answer, you'll get it right.
Yeah, hopefully. Just have to. Yeah, we just have to hope. But the solution had like 1,000 pages. 23? Yeah.
7 pages,
Yeah.
they 7 pages because we stuff for the students.
I mean,
in the industry other than teaching here,
Currently, no.
just like, yeah, no.
I did start, when I first started teaching here, I was working in.
You think like working in industry is better than teaching or
What is?
it's better like teaching or better to be in the industry, work in industry?
That's hard to say. It depends on what company you end up working with, what kind of projects they have, and I mean, teaching, in some ways it's easier. You have less responsibility for, I mean, the compensation for the responsibility is a better ratio, right? You're less likely to do something that will, uh, go end up in court when teaching. But at the same time, it's fun to be the sense of accomplishment when you're involved in a project that, and you see the final output in the project, that gives you a sense of accomplishment that it's not the same when you're teaching. You don't, you can see theory, you can develop even research projects that are interesting, but you never get that sense of that I worked on that thing, you know? So they both have their advantages and disadvantage, I would say.
But do you think like during the teaching it create for you like networking?
Teaching can create networking. It depends if you're active in the community and in the presentation. The best, you should keep track of when there's like what your technical group does, uh, does presentations every month or so. And,
I noticed that from the LinkedIn, always three professors, they are very active and like for researches and like a professor, he is new, like almost the second year for him. His name is Diwang. And Professor Mamado, the professor, the one that we are taking with him course, Usmani. They are very active. They are always like participate presentation outside of Canada.
and that's always good if you can do that.
I have a question for you because I'm working with the city. Okay? Like my job in the city is conditional. Means if I get the PNs, if I will stay in the job. If no, at the ending of it, they will get me out. Okay. So but I graduated from long time ago. I graduated in 2012. Okay. Once I came to here, no one like I applied to many jobs and no one hired me for me to have any experience. I studied construction technician, finished construction technician in Algon. And the first phase that I get the job, in fact, it's the second one. The first one, but I did it is MRC, because I graduated with 3.96 out of 4. So directly they like research. To be honest with you, my knowledge is not good. And I have like he is free. The laptop is with him. For me, I don't like that.
What's that?
Like always you are like doing the programming, you have doing research. For me, I the everything by hand. Sometimes to be honest with you, I didn't understand like things, but if I use the pen, that's better. So currently my challenge is to get the PhD. I have the AIT, but when I applied in Ontario, they told me I have to do confirmatory exams. And this is one of the things why I joined the university. I joined the university just like to get maybe some courses so I can use them in the field to do the exams. But I found here in Ontario they are very hard, they will give you a hard time and they are not easy with the application.
Yeah, I don't know if graduate course can serve as replacement because it's based on the undergrad degree program. So I feel that the graduate course can give you 1 year of experience, practical experience. That's what you can get from graduate courses, but not necessarily you will still need to do the exam.
But even if it's outside of Ontario, as the, I'm sure Ontario, they are very hard. They will ask you this sharply, you need this. But outside of the province, let's say Saskatchewan or any other province, they will not, because I have the West, okay, and the course by course evaluation, they are good. But in terms of Ontario, they refused the West. They will tell you, no, we are not accepting West. I believe in other provinces, they have the same rule. Or it's the
No,
PNG, it's like.
It all depends on who's
It
assessing you,
Yeah,
because if you get assessed for some scope of practice and they say you have the transferable degree, but you need to take these courses in this test, then whoever's assessing your scope of practice is the one to say what exams you have to take and because say you're a technologist, right? You have a diploma from college and you want to go up. The PN in charge will tell you what they feel.
They give you limitation. They will give you limitation, not like
Yeah.
as big. It's
Yeah.
engineer.
But they will tell you which courses you need in order to get to that level, and then that will determine what tests.
Knowing that, look, I'm not using anything related to engineering with this. I'm not signing that like ethical or something like that. I'm signing that the.
I would say a lot of PNs don't sign off on anything. What I could see anyway. Unless you're doing design.
From to get license.
Why didn't I?
Yes, why you didn't apply together?
Because I need 1 more year of experience.
So you have it 3 years so far.
I have 3 years and I have 5 years of construction. But they have to be under the supervision of a PN or related. So yeah, they say PhD is 0 to 2 years. So for me, that would be.
So. Yes.
It depends, it depends. I don't know, have you ever had a student get their their last requirement for the PN from the PhD?
not that I know of, no.
Question two.
Anyways, let's just get at least this set up and we can, so in this case, what we're going to do is you just use the strip footing. Obviously, we're going to be in the middle, so we'll have twice, we'll use the symmetry. Over this, and then under the edge here, delta becomes 0. And the beta will be basically the depth will have the tangent of beta will be I think we said it was a 2 meter wide.
Yeah.
It will be 1 meter divided by the depth. Give us our angle beta. We'll use a delta of 0. We'll use twice the influence value basically. And with that that value and
Excuse me, why you take it like the point?
I'm just using the elastic. This is based on Boussinet elastic theory, right? We're not going to do the calculation of the stress change with depth, because before what we did, we assumed a very wide loaded area and we had 10 kPa increase everywhere. This time we're going a bit more refined. We're going to look at the strip footing, 2 meter wide, over 8 meter depth. What's the change in stress at 2 meter intervals? I know it's coarse, right? We should probably decrease that, but we'll see. We'll play with the numbers once we we'll set it up for 2 meter intervals and then we'll look at it and decide how much finer we make it. Yes.
Isn't there like a depth of influence that we would want to,
Well, normally the depth of influence is used when you're not kind of simulating the stress distribution with depth. It's more the methods that look at the maximum depth. Ideally, you should have a degradation of the effective, and at some point you just get zero deformation due to your stress increase, right? In our case, we're going to assume just elastic enough stress, and we'll see what we get. So based on these, let's make a new spreadsheet. So just next, strip footing. So and so we start again, thickness. Have 8 meters. Then we have CV 1.10. Where it's here. And we have the Z meters. So, P. We say 1 year. We have 4. And then we can find these. Yeah. Okay. And now we have R. R is equal to CV times the T divided by that. And values that we had before. More than 1.5, so we're good. And we are now going to look at the stress distribution with, so here let's look at the depth. Good. Stress distribution, so we said it was 50 kPa surface. Look at the equation, we said that stress at a given under a given point is 1/5. 1/5 beta plus n beta cos beta plus 2 delta t. Delta. Plus 2 times delta, sorry. Okay, so that is equal to the first value. Divided by 5. And now we need to find beta. Okay? So let's calculate beta first of all. So in our case, we said that delta was 0. Delta. 0 everywhere. Beta. We said B is the footing width, it's 2 meters. And it's what we said, it's the degrees arc tangent of B over 2, right? Divided by Z.
Yeah.
Doesn't matter for the first one, because we know what stress is. That's in degrees. So here we say that is equal to this over pi times beta plus sine beta cos beta plus 2d. I'm assuming that beta there is supposed to be expressed in radians, right? Because if we use it as a scalar, has to be it has to be radians. And so we have radians of beta plus sine of beta times cosine of beta plus 2 times delta. And the problem is that I need to say twice because it was by 2. That's the stress, the increased total stress at different points. So at time, of course, our initial pore water pressure excess is initial pore water pressure excess is given by these values directly. But the thing is, because we have boundary conditions, we have it's dual drainage, so the the boundaries at zero immediately. That is that plus delta. And let's do it in terms of, we do it matrix wise. And compare with implicit. Let's see how it gives us. Okay, so if we go matrix wise, we said it's R, so 1, 2, 5. And that should be R. Another R. Minus R. R. And should have defined everything with zeros. Let's go and most and with transpose. Okay, so this is what we get in terms of year of displacement, maybe. Is it? Or would it be the same thing with the visit? So we define this is minus R. Plus 2 times R. I suppose multiply inverse of M. That is 0.23. 1.5. So there's a substantial difference there from the predictions.
So everything is based off of your M matrix, whether your M matrix is implicit or explicit. The difference
Well,
between,
not just that, is that, yes, the M matrix, but the M matrix is inverted,
yeah,
while the N matrix is not.
where it's used as the initial
The
condition.
relationship, what is related to the what? By inverting the M matrix, you're making it more complex, which of the previous ones are connected to the next ones, right? It becomes an intricate weave.
Hmm.
Just because it's an inverted matrix. Means that you have different nodes now coming into play.
So it's the time steps which cause I guess the main difference between the results.
No, it's because you get, like, if you look at our previous one. Because everything was constant, it's a little bit easier to see, but, let me. So. Let's change time step here to 1 year. Notice how there is. Just use the. Laser pointer here, okay, so here, right? We. We cannot have any movement in the explicit one until we start moving. Until the time start going by, because we're only affected by the direct neighbors. The implicit, because it inverts the matrix, you have a complex relationship between not just the direct neighbors, right? The direct neighbors were associated in the initial matrix, but that's at a future time step. But because you invert the matrix, if I look at my. Now. Because we haven't had a look at the inverter matrix, so. Let's do that just now, okay, so. Okay, so that's the inverted matrix, so. What does it mean? It means that your next. Okay. The next. This vector. So now. U0 is a function of. All the other nodes. Not just its own neighbors. Because there's terms here. So the expression of this is a function of U1, U2, U4.
And that's where in the implicit, we have the shift. That's why we have the shift in the implicit.
Well, that's why you have the shift, because it's affected by all the others in the. Okay, by inverting, you can see that, so. Well, not the first row, obviously, it's only affected by itself, and the last one also, but one is a function of all the other nodes. Function of all the other nodes, not just the immediate neighbors.
So one question for this is, if this is the case, should we perform one more time step in the implicit versus the explicit method? Because
Not really, because it predicts, see, it moves further. Cut up. To the time, so there's no restriction in that sense, but yeah, the explicit, we will really. Only really looks at its immediate neighbors, this one looks. In a more general.
Yeah.
Broader sense, the overall.
Yeah.
The overall set. Okay. And the Crank-Nicholson is literally the average between both. Yeah, that's basically what it is. You take the explicit, and you average them. You get Crank-Nicholson. Practice, that's what it turns out to be. That's why rho is R over 2, right?
Yeah.
Okay, so that is why what we're getting. So let's have a look at what we're getting here. We get let's put graphs. So again, it's not the prettiest in the sense that we have very few points. We'll have to try to. Yeah, well, instead of going too far, what we'll try to do is set up a new sheet with the same problem but with more values. So you can see the distribution, I mean, obviously the stress distribution goes to at the under the center should go to 50, basically. So it still goes up technically. But it has this shape, right? The stress distribution. So typically, so if I have the ground surface there, and I put, so if I want the stress distribution on the center of the load there, right? So the stress. So now I'm just going to plot the stress, not necessarily in terms of space, but it will look something like. That's the kind of shape that you're getting under the stress. So that's basically what we are witnessing here, but with the very coarse resolutions of 2 meters. Okay, but what's interesting to notice is that look how it becomes, it still centers and it becomes no different than what we had before, right? It's like centered in the middle of the layer there eventually. So you will have initially not just drainage upward, but it will move, the pressure will also migrate downward until you get symmetry and then it will continue that sense. So you get very interesting distributions of flow pressures. Let's do the same thing with this one. So we get very similar things. The shapes are similar, but obviously the data will be differently varied. In particular, notice how that red line there is very different in shape. The second step in one case crosses and the other one barely touches, but you get that impression that the distribution and eventually you become symmetrical from the center of the of the clay layer. Get that symmetry eventually. So that pulse will distribute and then make much of a difference. Let's see. What happens if I want to reduce so we said that R smaller equal to 1/2 or equal to B delta T over delta squared, right? So if I want delta T to be around or if I wanted delta T to be or what the value of delta Z would we want to have?
1/2?
One. Like we are trying to make it like a closer.
1 meter or 1/2 meter maybe?
I like half a meter for 1 meter. Well, if we wanna get a higher resolution,
Yeah, okay, let's go half meter. So what value of delta T do we need? We need delta Z, oops. Squared. Divided by 2 times CV. Must be smaller or equal to 0.11. Basically a month and a half. If I say 1 month. So we'll say 1 month.
yeah.
So if you're taking a time step of 1 month, and go with 0.5. We're gonna have bigger matrices. Get me this. Hey. Huh? That is talent, right there. Luck had nothing to do with it, nothing at all. So we'll just copy this. So we're getting close to 50, makes sense. Looking for. Obviously, that. Of 0 at the edge because dual drainage. Gonna do all this. Okay. Start from the bottom, maybe? Yeah. Not changing part of an array, right? Everything. Change on the part of an array. Yes, but that's the whole thing. Very tricky sometimes to erase arrays.
Does the array start at 0?
Yeah.
Oh, sorry. You're correct. Forgot I had my 0 there. Okay, so if this is 1 year, have to go to years. Let's see what we get. So how many we have? We have 17 items, so we need a new array that is 17 by 17. Okay, so 0. Right, 17. And if R course, I could start putting indices there and doing a check and conditional formula. If it's equal to the index minus 1, then it's R index plus 1. It's, so I could check the row and the column and automate this, right? This would be the smart thing to do. Am I going to do it the smart way? Still small enough that I think we can brute force it.
But you'd already need to have one of these done to do that, right?
No, you could just say. Yeah, maybe I should show you a trick then. What I meant. I could have just and here. So 4, 1, 8. So I could yeah. Have here a check. So if this so if the index, so if the index is equal, then I say 1 minus 2R. So if this is equal to that, 1 minus 2R. If
Yeah.
this is equal to, or if this is equal to that minus 1, then it's R. If this is equal to this plus 1, minus R. Otherwise 0.
Yeah. That thought you meant like computing, yeah.
This,
I meant like computing the implicit all in that for some reason, but no.
well, let's do it this way. Let's just increment all. Do it. To show how much we can start automating the node generation, because that's basically what you have to do once you start having any nodes. You have to start automating, whether it's programmatically or this way. So you say the row there is equal to, I can say, or the row there is equal to 1 minus 1, or is equal to that plus 1, then R. Else, if that equal to the column there. 1 minus 2 times R. Right, else 0. In theory, there, we did it. We did it. We did both the brute forced way and the automatic. Tri-diagonal. And that is how we now redefine. We said that this would be n. Say it's going to be AJ. 18. Okay, so now transpose. No, M mult. Transpose, that's multiplication. M transpose. And should have left the column. On the empty column right now. Yes, job. That's not defense. So I guess we see what it's all about. It's interesting that you see that we do get a crossover of the pressure, right, as balances. So that's an important thing to keep in mind as an engineer, though, that over time you will not always get the decrease everywhere of pore pressure, right? As pore pressure dissipates, you will get in some areas near the center an increase in pore pressure that will be higher at times further down the road than it is at time 0. So you have to keep that in mind for your design. Okay? And there will be a period of time where here, so you cannot design for this pore pressure in the middle of the clay layer. You have to design for the highest pore pressure you're gonna get. So this is one of the things that you get out of these simulations that you may not get. So even as a designer, you might be tempted to use just this pore pressure distribution. You know, for design purposes and so on, you want to be, you think you are being conservative by using time equals 0 pore pressures, right? And if you look at this, what this tells you is that you're not being conservative by using pore pressure distribution at time equals zero.
So what exactly is causing that? Is it just,
The fact that here you have high pressures. How does pore pressure dissipate? The pore pressure doesn't say, oh, this is closest to me, so I'm gonna go that way. Looks, less pressure this way, so some water goes that way, water goes that way. It's just trying to balance it out, right? The fact that you have this asymmetry in your pore pressure distribution, it's much higher. The increase of the excess pore pressure is much higher here than down. So here you have this asymmetry that suddenly goes down sharply. It will distribute itself before it starts moving back here. Once the pressures get here, then it starts redistributing this way because it has moved. Right, it just. Water
basically what you're saying is with the depth, right? See, I don't know, stress.
At time zero,
At time zero,
near the middle of that clay layer here, at time zero is not the worst pore pressure you're gonna get.
so if you were doing this as a design and you just get your pore
If you,
pressure right
at
there.
time zero, yes, you're not being conservative by using pore pressure in the middle of the clay layer at time zero. Okay? So that's 1D, okay? Now it's important to go into the 2D and to see the effects because it makes it a little bit more complicated. Okay? But this gives you a nice idea already, things doing these simulations, things that maybe we haven't touched usually in undergrad, right? But these are considerations you should think about when you're doing a design. Pore pressure, if all you're doing, you're not changing groundwater table, all you're doing is increasing the load because increasing load increases pore pressure much more near the surface than at deeper locations. In deeper locations, over time, you will get an increase. So the initial pore pressure distribution, which you would estimate as the blue line, just using the elastic theory that Boussinet method, right? Is the blue line basically. It would not give you the most critical stress distribution or pore pressure increase. Okay, so that's an important little detail to keep in mind when you're doing these analyses. And oh yeah, we messed up all of our implicit. We're not gonna do it twice. We're just gonna keep this because next thing we're going to start talking is how we handle 2D, I think. And
We're going to do this in 2D next week.
yes, it's basically the idea that we are planning to do.
And this is, sorry. This is vertical stress.
Yes, this is we're considering the effect of vertical stress. And then
But how would it be handled in 2D then?
okay, if you're doing it pure 2D, 2D assumes a strip footing basically. That's the basic assumption in 2D. Otherwise, you need to go 3D. If you want to have a finite width, a finite length footing, you have to assume 3D model. Where the seepage can go. So there's two things. One, to some degree, it slows down the pore pressure under the center of the footing. It should reduce pore pressure dissipation directly under the center of the footing, right? Because you have the water cannot leave directly under the footing. Okay, by doing 2D, you're now adding that need to skirt the footing to be able to exit. At the same time, you're now allowing water to move laterally everywhere. So my guess is that at that middle critical location would not be as critical because you would have more dissipation. The shapes will be similar to some degree, but you should get less of an increase near the middle just because you have room. The wider you make it, the more increase you will have under the center. The narrower it is compared to the thickness of the clay, then the less, and maybe you get no increase compared to time zero, but the wider your footing is, then the higher the chance of getting an increase there, right? So that part already starts taking shape when you do 2D. You're allowing flow laterally. And then when you add 3D, you don't get as much stress from the sides because it's a limited footing. And at the same time, you have now more area, so you should get faster dissipation overall in 2D and 3D because of that in other directions. In 1D, you're stuck to one direction. And then
So
if you
even if you do have dual drainage, it's still confined.
yes, it's partly confined on top. But yeah, dual drainage is more confined also than 2D where you have movement. And in particularly when you have seams of higher hydraulic conductivity material, you may have little seams dispersed in your bedding. And that will have an effect on your seepage time. So if you have tiny seams, you should expect more pressure to dissipate faster, which is very important when you are actually doing an excavation. When you do an excavation in clay, if you're doing on-drain shear strength, you're relying on your clay maintaining a certain strength. But the thing is, when you are doing an excavation, you're reducing stress, right? So over time, you should expect your clay to lose strength because pore water will migrate towards, because you've removed the loading, you get the suction. Remove loading, all the change in total stress is instantaneously carried by the pore water pressure. That's why here we used as our initial pore pressure, right, at time zero. Calculated, we find our total stress, or QZ, that's our change in total stress, right? Caused by our loading. Then we said, well, at time zero, that's exactly the same, that's carried by the pore pressure. Because I put the load, instantaneously I say pore pressure carries the load. When you do an excavation, that's a negative load, so you have a decrease in excess pore pressure, which means that over time, water will migrate towards the excavation to compensate for that suction. So over time so you cut in clay, you have a nice vertical wall, and over time it starts sagging and eventually it fails. Okay, so even if your retaining wall should not take into account the on-grain shear strength of clay, right? You should consider.
What do you mean suction towards,
Because if I have a negative total stress, if I excavate, I'm creating a suction in my clay. I decrease the pore pressure, right? But the clay surrounding, the soil surrounding it still has the same original pressure. So there will be a migration of pore pressure toward. So over time, you will be decreasing your effective stress. So you may have a safe excavation. Actually, they had that problem in Boston, the Big Dig, where they had used on-drain shear strength parameters for the clay. And they designed their shoring based on that. But all the seams, like you need to be certain that your clay will keep its strength long enough, right? So you can do a pore pressure distribution, but you need to make sure you have a proper view of the whole profile.
why would they only pick undrained?
My guess is that they estimated the hydraulic conductivity of the clay, figured out how long they could keep an excavation open and stay safe. Okay, but that's based on samples, probably lab tests. The problem is that they missed the little seams of sand and silt that were in between.
Oh, then water was just coming.
That's the problem with lab tests. Okay, it's better to do hydraulic conductivity tests on the field because you're more likely to catch those little seams that don't show up when you take a sample. You know what you're gonna do to take a sample? You clean it up, right? You take a silt seam won't let you pick up a nice sample, right? Or a sandy seal, it will break at that point. So lab tests done on clay like this will give you a false sense of lower hydraulic conductivity than what is applicable in the field, because when you have little seams, and this is where doing these simulations can help you figure out what, once you start doing 2D and 3D, we'll let you take that into account.
Any ideas?
So, but yeah, those little things, see, these little simulation games that you play is, it's not bad, and it gives you a feel, it starts giving you an intuitive feel for what you get from your, to expect from these, from your data. Anyways, we'll leave it at that for today. Next time we'll come back. I'll let you build for that same strip footing. We have the equation of the stress distribution of the, under a strip footing. I'll let you build me a 2D use symmetry from the center towards one of the sides, right? So it's gonna be only 1 meter one direction. So we definitely need to go finer resolution than one. So 0.5 was the bare minimum we could do, I think. But yeah, so next time we start looking at that, and we'll see what kind of results we get. Okay.